You have a roller coaster with a scale model. This is a scale model of a roller coaster. You got the cart mass, you got no friction, with an initial speed of 1.5 meters per second at the first hill of height 2, and then you're going to go from point starting to point A.
Attention high school teachers, we have a little announcement. Varsity softball players, please report directly to the bus at your checkout time when the bell rings. Lunch will be provided on the bus today. Varsity softball players, when you check out, report directly to the bus. Lunch will be provided on the bus. Thank you.
First point is at the start of the thing. Second point is where your problem is finishing. So the energy values at those 2 points must be equal, according to conservation of energy. If friction then adds another piece to it, we're going to have to go through it another day because that adds work. So you can still do the problem. Let's suppose you had friction. Total energy is going to be equal. Use K at the beginning. So mgh plus 1/2 mv squared. And that's going to be equal to the energy that we had here, and 1/2 mv squared, plus work done for friction. We will do friction problems with work another class. That's adding another thing to it. But for right now, just focus on how we solve energy problems. Identify your points. Identify the energies at both points. So here, we're moving, so we have kinetic. We're at a height, so we have potential. At our second point, it is assumably moving, since we're calculating the speed. And it is also at a height. So there's our conservation of energy equation. All the kinetic and potential at the beginning equals all the kinetic and potential at the end. Kinetic is 1/2 mass at the beginning squared. Height at the beginning. Mass at the second point squared. Plus height at the second point. Everybody's got a mass, so we can divide it. We're solving for this guy right here, the velocity at point A. So we want to isolate him, get him all by himself. Multiply by 2. Actually, let's move that over first. Now we multiply through by 2. V1 squared plus 2. GH1 minus 2. GH2 equals V2 squared. And like we looked at in the previous problem, V1 squared plus 2G H1 minus H2 equals V2 squared. That's our old kinematics equation. It doesn't matter how high up you are. It just matters the difference in height from where you started and where you finished. So we could have just as easily said, let's call this height equals 0. It doesn't change our problem because all we're talking about is the difference from where we started and where we finished. We don't have to set ground level at 0. We can set that height at 0. More on that and more problems. Initial velocity, 1.5 meters per second. Square that, plus 2 times gravity, times the difference in height. We went from 2 to 1.9. So the velocity there 1 times 2 is 2. 1.5 squared. I don't know. 2.25 plus 2. 4.25 meters per second. Square root. Of course. Square root of 4.25. 2.1 minus 1 for me. 2.1 meters per second. It's going faster than it originally was because it went down. Basically, gravity pulled it down a little bit and no friction acted on it, so it's going to speed up. The lower you get, the faster you're going to go. This would be the maximum speed point. Part 2 changes gears a little bit and turns it into a circular motion problem. What forces do we have at point A? Normal and mg. That's it. They're centripetal forces because we're going around in a circle. So when we do part C, I guess, calculate the magnitude of the force of the track. What's the force of the track? It's a normal force. mg minus the normal force equals mac. Circle motion, so it's centripetal. mg points towards the center of the circle, so it's positive. mg minus normal force equals m v squared over r. mg minus mv squared over r equals the normal force. Oops. Velocity at point A is 2.1 meters per second. Quantity squared divided by the radius of the circle is given to you as 0.95 meters. Equals our normal force. .7. Newtons, since it's a force. So is it touching the ground? Is it going over that circle with contact? Yes, because the normal force is greater than 0. If that normal force went to 0 or less, then it would leave the ground. And how could we make it? Nope. Anytime that the normal force goes to 0, it can't be touching by definition, because in order to have a normal force, you have to be on the ground. And if you're on the ground, you would have a force exerted from the ground.
So theoretically, if there's no normal force equals 0,
you're not touching the ground anymore. That represents, the normal force represents the turning point, where you go from touching the ground to 0 point where you're not touching it anymore. It's kind of like it's a limit, I guess. If we wanted to stop the car at point A, what do we have to do? Introduce friction. How much? Not actually, we're not actually asking how much friction, but how much work. Is that it? All right.